Hi, I'm Sharon Richardson, and this is a short talk to introduce some of the different ways that bias can be present in data and how machines can learn to make the wrong prediction. The focus is on real-world data. We build models from such data to discover insights, to tell us something about the world, and use it to predict what may happen next in a given situation. Bias matters. The talk is based on a paper I wrote that was published in 2022 called Exposing the Many Biases in Machine Learning. This is not an exhaustive list. The purpose is to give a general understanding that bias can enter data and algorithms in many different ways. Number 1, completeness bias. The dataset is incomplete and missing data that would improve predictions. It's rare to have complete data, what we would call a perfect population, so we should always be asking what data might be missing and how do we account for that. Perhaps the most famous demonstration of this is Abraham Wald's work on aircraft survivability during World War II. US statisticians were tasked with identifying where to reinforce the planes without adding too much weight, so they plotted the damage on returning aircraft. Abraham Wald questioned where the damage might be on the planes that didn't return. And perhaps instead of protecting the damaged areas, the focus should be on the undamaged areas, the engines, the cockpit. This is also known as survivorship bias. It occurs when the data that you have is actually a subset that has passed or survived some selection criteria. It is biased. So fast forward to more recent times. In the early days of large language models from 2017 to 2020, most were open source, and a 2020 paper detailed what was then the largest training dataset, known as the pile. I went through that paper to categorise the sources, and you can see the results in this pie chart on the right. The dataset was mostly English, mostly US based, and with a high proportion of specialist technical content. Is this fully representative of human language and culture? What data might be missing? How might that impact what language or style of language the model goes on to generate? Number 2, representation bias. Is the data representative for the purpose it is going to be used for? Back in 2018, it was revealed that Amazon had built an algorithm designed to automate recruitment, and then scrapped it because they couldn't stop it from being biased against female candidates. Removing gender information was not enough. It was based on 10 years of applications and hires, technically a complete data set. But over that past 10 years, most of the hires had been male and most of the applications had been male. So it meant there was a very strong skew in the distribution. That means it's going to be very hard for anyone to be selected who has attributes that are uncommon or not present at all in that historical data, no matter how well qualified they may be for the position today. The model will only predict based on past performance. And you can think you have a balanced distribution of data and still have problems, because with real-world data, there's lots of details, fine details, that can impact on predictions. In this example on the right, it's one of the earlier computer vision algorithms, and it was actually created to demonstrate how easily an algorithm could misidentify the object of an image in a way that a human never would. The algorithm in this instance incorrectly classified a husky dog as a wolf, not because of any features of the dog, but because there was snow in the image. The dataset had the same number of images of husky dogs and wolves, but snowy backgrounds were only present for some of the images of wolves. And so the model learned that the presence of snow must mean the animal is a wolf. This is shown in the explanation image on the right. The greyed out pixels show the areas of the image that were not used to make the prediction. The prediction had nothing to do with the features of the animal and everything to do with snow. Number 3, truthfulness. A lot of real-world data contains inaccuracies. There is plenty of research that's been published to show problems with relying on surveys to understand human behaviour. When we know we're being observed, we tend to behave differently. When we're asked embarrassing questions, or when we think a truthful answer will cause people to form negative opinions about us, well, we can be economical in our responses. A classic, often quoted example is that when the doctor asks you, as an adult, how much alcohol you consume per week, they will assume it is double whatever you say. But also, we're a social species. Most of the time, most of us want to get along with each other. We often use half-truths or white lies to avoid hurting someone's feelings. We probably lie to some extent a lot more often than we realise or would even admit to ourselves. And this has been termed the social desirability bias. And then there is deliberately creating misleading data, often called adversarial bias. There have been studies testing how many bad examples are needed to poison a training dataset, or how to design data specifically to trip up a prediction model, such as wearing clothing or accessories with special markings that are enough to make a computer vision algorithm misidentify you as something else entirely. But this example on the right is actually more of an art project. The artist wanted to see, could he create a fake traffic jam alert on Google Maps? He bought 99 Android phones, put them all together in a small cart and wheeled them around the streets to see what happened. Number 4, subjective bias. We've mentioned that people may cause bias due to the flaws in their responses or their behaviour in the real world, but the observer's recording data can also create distortion by deciding what does or does not get captured. In 2019, a paper was published aiming to build the most comprehensive and accurate database of notable people from 3500 BC to 2018 AD. And its source? Wikipedia. That created a slight problem because Wikipedia was already known to have a bit of a gender bias problem. Most of the editors believed to be male, as many as 90%. Most of the biographies written about men. And at the time as well, there was increasing awareness of just how many notable women had been written out of history, and inaccurate assumptions about the role of women historically. And a lot of this has been changing since. But the reality as well is that creating a truly fair and representative real-world dataset can be incredibly challenging. By its nature, much of the data we collect is subjective, including to its position in space and time. This 2021 paper on the right highlighted the challenge, looking at the placement of air quality sensors in the city of Newcastle in England. Whilst there was good coverage in the city centre, you can see a cluster of dots down in the bottom middle of the image, the placement in suburbs was much more sporadic. And if there is socioeconomic bias in where sensors are or are not placed, that can create inequities in policies and decision making. A good colleague of mine, Dr. Andrew Bullmore, describes this as the challenge from analogue to digital, how important it is that the frequency and fidelity of data is fit for its intended use. The first 4 biases have mostly focused on bias within the data when it's captured. Now we move on to how it is curated. Starting with labelling. Data is often annotated and labelled for training, and much of that labelling to date has been performed by humans, which means the labels will reflect the human labeller's perceptions and biases. This was highlighted in a 2019 paper that found issues in using algorithms to detect hate speech. African Americans were found to be up to twice as likely to be labelled as offensive due to the labeller's insensitivity towards differences in dialect. And this was captured really well at the time in a tweet on the platform formerly known as Twitter. I need people to understand not all cultures communicate the same way. In my culture, it's very normal for people to talk over, interrupt each other, and it is not automatically considered rude. Stop attributing personality flaws to people because they don't share your cultural norms. Very powerful statement that highlights how challenging it is to even label data fairly. And can the machines do better? Well, this image on the right it's based on a joke that was posted online. Would a computer tag this image as a single very long cow stood behind a building? Because a human would instantly know that is just not possible. It must be 2 different cows. Otherwise, you'd need extra legs to support the spine, and we've never seen a 6 or 8-legged cow yet on planet Earth. Algorithms can often be found to have blind spots that only show up in application. And yes, they can be usually overcome with more and more training, but only once we're aware also of those flaws. And there's a risk it could lead to serious consequences. In 2017, somebody posted a picture to Facebook with a caption in Arabic that said good morning. The Facebook algorithm mistakenly translated it in Hebrew as attack them, and the poster was arrested. Fortunately, the error was discovered and he was released. Could have been tragic. Number 6 is biases that are inadvertently introduced when manually rekeying data across systems and when cleaning data for analysis, when we actually edit the data itself. A study back in 2015 showed that on average 12,000 people are wrongly declared dead every year in the US because somebody enters the wrong social security ID. That's an average of 33 a day. And actually that sounds bad, but it's an error rate of less than 1%. But nonetheless, as algorithms become more targeted and systems more automated, these errors can persist and become problematic. It can take years for them to be corrected, leaving a living person who has been incorrectly declared dead in administrative limbo. A more common risk is inadvertently introducing errors when cleaning data. Real-world data often contains errors or missing values, and when facing incomplete or suspect records, a decision has to be made. Do we keep the record as is? That can be feasible if the dataset is large enough to smooth out occasional errors. Do we delete the record to guarantee accuracy and purity of the dataset, but risk reducing it becoming too small to generalise from? Or do we impute a value in place of the missing or incorrect value and risk inserting an error? And this table on the right, this is actually from my PhD. It's a real-world dataset, daily weather readings from a weather station in London. And it had all sorts of problems in it. It had values that could be considered anomalies or outliers, but yeah, they're really important because it's actually taken from readings in August where overall you'd expect the weather to be dry, but you might have a sudden thunderstorm with very heavy rain, and that is shown up in the precipitation values. We've got interesting averages to consider. Do we want average temperature? Well, is that over 24 hours? Because we probably want daytime and maybe nighttime averages separately. But the big challenge is when you get a missing record. And the third one from the bottom is exactly that. And it shows the whole range of what can happen when the sensors aren't working. Some of the readings, they're just null values, so there's no values at all for temperature or humidity. We've got an impossible value for the average dew point, which can often be done deliberately, so you can pick up when there's an error, you put in a ridiculous value into the field. And then we've got what look like quite reasonable default values, but that might be true for the barometer readings because they're not far out from the rest of the readings in the dataset, but it's completely hopeless for precipitation, rain, because it might not have rained at all, or it might have had a torrential downpour. So what do we impute into that? These are the challenges where we can introduce some errors into our predictions. And even if we've captured the perfect dataset and we've curated it without introducing any new biases, we can still unintentionally introduce bias at the modelling stage. In 2022, Nature published an article showing numerous issues with the poor use of machine learning methods in research papers. It spanned 17 academic fields and collectively affected over 300 papers, and some of which could, quote, lead to wildly over-optimistic solutions. And this is in research. How can this happen? Well, there are many points during the machine learning process where we can bring in errors. Categorical data will need to be transformed into numerical formats, and that can create inappropriate weights. Imagine that we've transformed some data to the values of 1 to 12. Well, from a weighting perspective in an algorithm, we tend to treat numbers as distance, so 12 is further away from 1 than 6, and that might mean something. But then what if I tell you that 1 to 12 actually represents months of the year, January to December? Well, if we're looking at seasonality, January's got a lot more in common with December, number 12, than it has with June in the middle of summer, in the hemisphere where the UK is based. So it matters. We need to think about how we handle that. If we are doing feature selection, there is a risk if there's bias in our data, we will amplify it by focusing on the features that actually contain the bias. Or we might think we've managed to remove it all, such as with the Amazon study. We've stripped away all gender references, names that could infer gender. But actually, if we've kept in college names, well, if there are male-only colleges and female-only colleges in there, we've still got gender in the data set. It's actually quite hard to remove it completely. There's enrichment, where we actually create new features by combining some together across data sets and can accidentally bring in spurious correlations. Sampling is a big one. We have our data set and we will split it into training and test so that we can test the accuracy of our prediction models. How you do those splits matters. Random, Random split sounds reasonable. Well, not if you've got a few outliers. You might want some in your training and some in your test, and you can do that with what we call stratified random sampling. But you can do arbitrary cutoffs. Some people forget to split at all, as was found in that Nature paper. There was actually quite a few instances where an algorithm had been trained on the data and then tested on the very same data. You will overfit. That is an incorrect method. And then there's the algorithm choice as well. Take one approach, which is clustering. If we want to understand that there are clusters of readings within our data set, well, there are different types of clustering algorithms, some of which will deliberately include all values, including outliers, some that will deliberately exclude outliers. So whether or not outliers matter is an important decision. And then we've got our perfect data, we're ready to create a perfect prediction model and start using it in application. How long will it be good for? The predicted performance is very much dependent on being applied within the same environment that the model was trained on. But even a specific space will change over time. To give a simple example, Waterloo Station in London has historically been the busiest commuter station in the whole of the UK. So let's say we decide to train an algorithm based on the content of photos. We're going to use computer vision to estimate how many people are present and then predict. Well, if we did it based on 1900s, we get lots of horses and lots of hats. Move to the 1980s, there are no horses and not many hats. In 2019, we were seeing a change over the daily patterns, what we call the Tuesday, Wednesday and Thursday peaks. And this was partly in the UK. They'd recently reintroduced the right to request part-time work, and it showed in the readings. We were seeing a tail off on Mondays and Fridays as people were tending to work from home on those days. And then, of course, 2019, go forward just 12 months, and we get a very different reading. Imagine running an automated system. You would want to intervene pretty quickly when COVID-19 lockdown occurred. Models based on real-world data are always situated in space and time, and their longevity is limited. So that's it, just some of the many different ways that bias can be introduced into prediction models. They broadly occur at 3 stages. When data is captured, is it complete? Is it representative? Could there be concerns about truthfulness of participants? Could there be subjective bias from the observers? When data is curated, unintentional errors created during editing and cleaning of the data, or when transforming or annotating data or enriching its features. And when data is used to train a model and make predictions, which features are selected, what sampling method is used, the choice of algorithms and methods, and finally in application, is the model fit for its intended purpose. And with that, hopefully you can see how machines can learn to make the wrong prediction. I've glossed over a lot of the technical details, but hopefully this has given an idea of some of the challenges working with real-world data to make predictions. With the arrival of tools that now make it much easier for people to build prediction models without first needing to train themselves as a data scientist, there is a risk we will see more biased models making predictions that, if wrong, could have serious real-world consequences. There are techniques to evaluate and test models and data sets for bias, but we really do lack the rigour that is commonplace in traditional statistical methods when reporting on the performance of machine learning models. Our prediction models often need to come with a warning: handle with care. Thank you for listening.